Ok, bonjour, bienvenue. Merci d'être venu. Welcome. Thank you for coming. So today we will finish the second quantization for two-body operators. And I will give a little example of how annihilation operators or creation operators evolve in the case of a quadratic Hamiltonian. So it will be a little bit exercise with commutators and so on that I will use later. And I will introduce the many-body Green's function. And the way I will do that is first to talk about angle result photoemission spectroscopy. And it will be clear that we can measure directly, not only calculate, but measure things that are directly related to the Green's function. So I will define it after I do this experiment using, again, the golden rule. And I will show you what happens in the case where the Hamiltonian is quadratic. And then we can calculate the Green's function and find it's the same as the one-body Green's function in the Schrödinger problem, and then spectral representation. And next time we will be ready to move in the complex plane. So is everybody okay? Are there any questions? Okay. So two-body operators. So this is an example here. I take 1/2, and then these are, and I have n particles, 1 to n, and u equals 1 to n. And this is the interaction between particle 1 and particle 2. For example, if I am in an eigenstate, which I will assume. So if this is position R1, interaction between particle at position at 1, and then particle at 2, and then particle at 3, and so on. And there's 1/2 because we're counting things twice if we do it this way. Now I don't want to take mu equals nu because then it's interacting with itself. Okay. So I assume that these are eigenstates of this. For example, if this is V of Ri, R minus Rj, these are position R1, position R2, etc. So suppose I have only 3 particles. Let's forget this, and let's see how this happens. This acts on this. So I need to, let's take mu equals 1. Then I have to see how it interacts with 2. So that's this term. And then to see how this 1 interacts with 3. Okay. Then I take mu equals 2. So mu equals 2 means that I act on this guy. And then the nu again goes from 1. It doesn't go through 2. So nu takes the values 1 and 3. So I have this term when I am looking at 2 and 1, and when I'm looking at 2 and 3, I have this term. And then I go to the last term. So this is particle 3 interacting with 1, and you see that the V comes in twice if I do it this way. So that's why there's no 1/2 here. So how do we write this in second quantization? So in second quantization, now remember we have a way to do things that are independent of the number of particles. So now the eigenstates are labeled by m, and I assume that there's an infinite number of them. So m goes from 1 to infinity, n goes from 1 to infinity. And then all I have to do is count the number of times that if there's particle alpha I here, so this operator will give me something different from 0 when the state, when m is equal to I. So this is counting the number of pairs of particles. But I need to subtract this because here I did not take into account the interaction of particle with itself. So for example, in this case, with the 3 particles. We have 3 times 3, so we have 9 terms, minus 3, so we have 6 terms, and we divide by 2 because every term comes twice, so we have 3 terms. Okay. So is it okay with you? Okay, so now the way this is rewritten in a different way usually. So let's write a C dagger alpha m C alpha m. So that's this operator. Then I have C dagger alpha n C alpha n. That's this operator. And I have minus C dagger alpha m C alpha m delta m n. Now I can do this. This I can use the anti-commutation relations for this, and I can write this. I can write this as 1 minus C dagger alpha m C alpha m. Okay. So if I do that, this one, I have m and n. It's not the same index. So I cannot write 1 here. I have to write delta mn. If m and n are different, they just anti-commute. So you see that this term here with this and this cancels that. Okay. So the final result is C dagger alpha m C dagger alpha n C alpha n C alpha m. And why did I lose the minus sign here? I lost the minus sign because I anti-commuted C alpha m and C alpha m. You see the m now is at the end. Okay. So if you have bosons, so where they commute instead of anti-commuting, you can work it out and it gives exactly the same thing. So it's valid for bosons and fermions. So you see, you need to avoid double counting, you need to destroy the two particles and create 2 afterwards. So that avoids the double counting. And in field theory, it's called a normal order. So the destruction operators are before the creation operator. It's just a detail. Okay. So in the case of, so if we rewrite this for the Coulomb interaction, and now I will even put spins back because I never talked about spin. So the spin can be contained in this eigenbasis, so up and down. So if I put spins back for the Coulomb potential, it's written this way. We have sum over spin sigma sigma prime, and then I have integral d cube r d cube r prime. Then I have the Coulomb interaction v of r minus r prime. These are labels, not operators. And now I have psi dagger sigma r, psi dagger sigma prime r prime, psi sigma prime of r prime, psi sigma of r. So this is in the same order as here. So that's the Coulomb interaction. Okay, because the density operator n is just psi dagger r psi r. Okay, so if I just do this correspondence, that's what comes out. Okay, so let's do now a little exercise for the time dependence of these operators when the Hamiltonian is quadratic. If you have any questions, go ahead. So take, for example, an example of a quadratic Hamiltonian is H operator, if you want, is equal to sum over some y vector, some label, epsilon k times a c dagger k ck. Okay, so this is the number operator, n of k. So the eigenstates of this will be of the form c dagger k1, c dagger k2, for example, acting on the vacuum. So this will count. So there's a particle in state k1, a particle in state k2. So when this acts on this, it will give me the same state times epsilon k1 plus epsilon k2. Okay. So so by the way, because while we're doing this, note that if I have interactions, then this cannot be an eigenstate. Okay, why? Because you see, this will kick particles out of, let's say, state 1, state 2, and it can put it back in different states. So it's right. It's more obvious with this, actually. I'll come back on this later. Okay, now if I want to know the time evolution operator, time evolution of one of these operators, for example, so I use the Eisenberg equation of motion. So I take I d dt of ck of t is equal to I d dt of e to the I h t c k e to the minus I h t. Is it okay? Ck of t is this in the Eisenberg equations of motion. So if I take the derivative, you see that what I get is I times I is minus 1. So I get minus the commutator of h with ck of t. Okay? So because here I get I get this on this side, and then when I differentiate this, I get the H on the other side. Okay, now H commutes with itself, and so it means that it does not evolve with time. So I can write this as epsilon k of c dagger k at time t times ck at time t. Is it okay? Because H is time invariant, and you can also just do this algebra and find that it works out. Okay, so it means that now I can use the equal time commutators. Okay, so if I use equal time commutator, I know that I have the number operator here, and I know that the number operator commuted with the destruction operator is minus the destruction operator. So with the delta function. So this is basically just minus epsilon k times ck of t. So the solution of this equation is just that. I will write it here. Is that ck of t is equal to e to the I epsilon k t times ck. Okay? This is the way to play with this. And this evolution operator is valid just because this is quadratic, right? If it was not quadratic, then I would have other terms. So it's important to keep this in mind. Okay, now that we finished this little exercise, let's move to angle resolved photoemission spectroscopy. So given my bad talents with pictures and drawing and graphs, I did it in advance. Okay, so what is angle resolved photoemission spectroscopy? Well, it's a photoelectric effect. So it means that you send a photon here on a material, and then an electron comes out. And then you measure the momentum. There's an h bar square here, so you measure the energy of the outgoing electron in free space, and you measure all the angles. Excuse me, that are coming up. So the magnitude here gives you information on the energy. More specifically here, the energy is the energy of the photon coming in. Plus, you will see that we measure the energy with respect to chemical potential. So it's omega plus mu is the energy that the electron will add in the material. And that's so-called work function that's related to surface effects. And we will not discuss the contribution of that term. Now you see I have emphasized here K parallel. Why did I do this? I did this because there is translational invariance in the plane here. So momentum is, this momentum is conserved, but not the one perpendicular to the surface. So measuring the energy and the momentum of the electron coming out, we get the energy and the momentum that the particle had inside the material, and we will focus on two-dimensional material, so we don't need to worry about the depth. So two-dimensional material just means it's highly anisotropic. So high temperature superconductors are in this category, for example, and many interesting materials are very anisotropic. They look quasi two-dimensional. Okay, so we just want the cross section here. So very simple experiment, but to get enough I mean, the coupling between light and matter depends on the fine structure constant, which is just 137. So to get a lot of electrons coming out, you need a lot of photons. So usually this comes from either very powerful lasers or from a synchrotron. So this photon can cost millions of dollars depending on how you do it, right? Okay, now I want to compute the golden rule, so I want to use a transition matrix element. So what's the interaction between matter and light? We know that it is this, right? We've worked on this before. Okay, so it can be written, let's write this in momentum. So it's equal to minus sum over k prime of j of k prime dot a of minus k prime. Right, that's Parseval's theorem. Okay, and now I can compute the matrix element for the transition. So I have the minus sign, and as you know, in quantum mechanics, we work backwards, right? We work, or if you want, forward. If you think of the Arab countries, right? We start from the right. So the initial state is to the right, and the final state is to the left. So let's write the final state. So the final state has some state of the system that I will call n, actually. And then the electron now is very far. So I will write, and it's basically a plane wave in the vacuum. So I will write it as a plane wave state. I will write that the final state is k. And also I have 0 photon. So this is the vacuum of the electromagnetic field. And then I have this thing here. So sum over k prime of j of k prime dot a of minus k prime. And now I need to write the initial state. So the initial state, initially the particle is not the particle, the system complicated state here is in state m. There's no electron in the vacuum, so I have 0 for the electron, and I have one photon in a state q for the electromagnetic field. So how does this work out? Well, it works out like this. If I look now just at the electromagnetic field, I have 0 for the electromagnetic field, and I have a of minus k prime, and I have one photon here in state q of the electromagnetic field. Now a of k is like the harmonic is if you write the equations of motion for the vector potential, you see that for each frequency it looks like a harmonic oscillator. So basically a is like x for the harmonic oscillator. So in a there will be a dagger of minus k plus prime plus a of k prime with curve prefactors and so on. But the point is that in A, there's always a way to destroy a photon here and go to the vacuum. Okay. Now, what is the momentum of the photon? Well, the photons carry mostly energy because if you compare with condensed matter, what happens is that the speed of light is so large that a given momentum gives a huge energy. So as far as we are concerned, the momentum of the photon can be taken equal to zero, basically. So so we will the only state that will contribute here is a k prime about zero. So now we need to work with this. So what is the current operator? Well, the current operator, J of k prime nearly zero, is a sum over P of P over M times a C dagger P CP. So that's a Q equals K prime equals zero. So it means that I'm looking at the integral d cube R of J of R. And now J of R I write with what we had before, the psi dagger, psi, and gradient, and so on. And so when I take these two labels have to be the same. Because of the dagger here, Fourier transform will have a different sign. Yes.
One question. Isn't there a charge missing?
Yes.
Okay, thank you.
Very good. Thank you. Okay. So if we do this now, you see what happens. The way it works here is that we will remove, so M and N, we will remove a particle from the system here with the destruction operator, and we will create this electron with that creation operator. So basically what we have is minus N C, okay, now C of K parallel. Why? Because we select the electron here to have a given K parallel, and it's conserved. So among all these P's, I mean, there'll be electrons all over the place, but we look in one direction. So this P is K parallel here times M. And then we have the rest. So we have the charge, and we have a K, and we have a C dagger K parallel, and we have a 0, and we have K parallel over M. So this is really sloppy because, I mean, I'm creating an electron in K, and here I just take K parallel. I start from the vacuum for this, and I go to K. But as I said, the momentum is not conserved around this, and indeed there are some subtleties here. But the point is that all of this is related to things that we know, just like a usual scattering experiment, and that's what we are measuring. Okay. So if we write the golden rule now, now we just need to, there will be 2 pi over h bar, and then the square of this matrix element, and then the sum over final states. So the differential cross section would be proportional to Okay, just like we did before, the initial state, we don't know, it's just a thermal state. So it means that we need to sum over m of e to the minus beta k m, where k is e minus mu n. It's h minus mu n divided by z. And then we have the square of this matrix element. So we have n c k parallel, ck parallel m modulus square, and then we have a delta of omega plus mu minus em minus en. So we need to conserve energy. So omega plus mu here, omega plus mu is equal to the difference in energy between the initial and the final state. And there will be we don't know the final state, so we need to sum over all the final states here, n. Okay. So now we use the same trick that we used before and replace this by the Dirac expression for the delta function. So we have sum over m n e to the minus beta k m over z times n ck parallel and m ck parallel dagger n and times the integral dt e to the I omega t. Okay, here I will, before I continue, I will do a little manipulation here. Let me write em. I'm sorry. Let's write instead Km is Em minus mu times the number of particles in state M. And Kn is En minus mu times the number of particles in state N. But now the number of particles in state N is one less than in state M. Okay, I go from M to N and there's one less particle. So this is N M minus 1, so it is plus mu. Okay, which means that I can write this as I can remove the mu here and write this as Km minus Kn. Km minus Kn. So I will have the difference in energy, and the minus with the plus will give me the mu that was here. Okay, so now I will do like we have done before, which is to write this as I to the I omega t times e to the minus I km minus kn t. And now I can put this as the time evolution operator of this. Okay, so in other words, this I can write as n e to the I k n t times c k parallel times e to the minus I k m t times m. Excuse me. You see what I'm doing? So this I want to take here. So the final result then is that this differential cross section is proportional to integral dt e to the I omega t times the thermal expectation value of, okay, this I can put here with the n. So I have c dagger k, c k of t, and that's it. Okay, so I move the time evolution operator to this. I took the integral over here outside. The e to the minus beta km that is acting on this this m here on the left is in the definition of this thermal average. Remember, this thermal average as the quantum mechanical trace and the thermal average. Now we will show in the next time or very soon that this is equal to the Fermi function times the spectral weight of the one particle Green's function that I'm about to define. Okay. So if we can measure this, we can measure the spectral weight of the single particle Green's function. Okay, so the details of the derivation here are not so important. They follow exactly the same pattern as what we did for at the beginning for a general scattering process. There's a little bit of fuzziness here in the calculation of the current operator and what happens really at the Fermi, at the surface, but let's take this as an approximation. Okay, so we move to point 2 here, the definition of the one particle Green's function. So we define it like this: G retarded of R T R prime T prime is equal to minus I times the thermal expectation value of the anti-commutator of psi of R and T with psi dagger of R prime T prime times theta of T minus T prime. So you see it looks like a response function. Remember, we had that chi retarded of t for the harmonic oscillator was 2i times chi double prime of t times theta of t. And that chi double prime was a commutator. Here we have an anti-commutator. So it's the response function. Here we were responding to some object that could be really classical, like an external force or a charge or something like that. Here it's as if we have the response to some external field that obeys Fermi statistics, which don't exist in the sense of on a macroscopic scale. We don't have the equivalent of a semi-classical field for fermion. We can define it mathematically. These are called Grassman variables, and we may come to that later in the class, but for now, just take this as an analogy. So all that I need to do now is to convince you that it's in the case of a single particle, we recover the single particle Green's function that we had before. So and there's another comment I need to do here, which is that in the case of the one-body Schrödinger equation, all the information was in the Green's function. I mean, the Schrödinger equation and the Green's function are completely equivalent. Here in a many-body system, we're just looking at how a particle propagates. We don't have all the information in a single particle Green's function. We just know how a single particle propagates. So let's take the case where we have just one particle, and these expectation value now are just average in the ground state. Okay, so they are average in the ground state, and then we have psi of RT, psi dagger of R prime T prime acting on 0 times theta of T minus T prime. And the other order gives me 0, right? Because psi acting on 0 gives me 0. So that's all there is. So what is this? This is minus I, 0. Now the time evolution operator that acts on the vacuum here does not give me exponential of 0, so that's nothing. Now the psi of R that acts on this state just gives me R. Now I have the time evolution operator to the right here, which is e to the minus I h t. And then the time evolution operator of this to the left will be plus I h t prime. So I have I h t minus t prime as an operator. T minus t prime. And then psi dagger acting on the vacuum gives me R prime. You know, the Hamiltonian acting on the vacuum is 0. So I have this. And I have theta of t minus t prime. Okay. So this is exactly what we had for the one-body Green's function. Now let's give some other examples. Again, take H quadratic, okay, the same Hamiltonian we wrote before, and assume we have just one particle, just an eigenstate of this object. Then this what we need to this, if we take Fourier transform of this, it means that we have to compute G retarded we assume translational invariance. So reach G retarded of K. And we have a time translational invariance also. So I will put 0, 0 here, and 0 there, and 0 there. So GR of KT is minus I times the expectation value of the anti-commutator of CK of T times the C dagger of K times theta of T. So now I kept this here, you see. So this is equal to CK. Again, just because we have a quadratic Hamiltonian, huh? Otherwise it wouldn't work. E to the I epsilon KT. And now this anti-commutator is equal to 1, huh? Okay. So I get minus I e to the I epsilon k t times theta of t. And if I go to Fourier space, then it means that G retarded of k and omega, again for this, just for this quadratic Hamiltonian, and this is 1 over omega plus I eta minus epsilon k, okay, which is again the form that we have. Now let's look at the more general case. Again, quadratic Hamiltonian, but don't pick plane waves, okay? We just go more general than this. Single quadratic Hamiltonian, and instead of momentum eigenstate, we have general states. So by using our change of basis, we know that psi, wow, okay, going on strike this time. So we have psi r of t is equal to sum over single particle energy eigenstates times r n e to the minus I e n t times a n. Okay, so we just use the change of basis formula. So this is the change of basis gives r n a n, and then we look at the time evolution. So if we look at the time evolution, this is an eigenstate, so it's the same thing as we just did for CK. Gives this with an energy against single particle eigenstates En of t. So this is equal to sum over n phi n of r. Okay, that's the definition of the wave function. E to the minus I en t times an. Okay. Now, if I do the same for psi dagger r prime, I substitute in this, what will happen? What will happen is just the same as what I just happened, is an and a dagger n will give me unity. Okay, so I will be left with G retarded of R prime T will be equal to minus I sum over N. Okay. Now there will be a sum over N here and a sum over M here. But AN and AM anti-commute unless M equal to N, in which case we get delta function. So that I have a single sum over N left. And I have phi N of R, phi star N of R prime, e to the minus I E N T times theta of T, which means that the G R of R prime T will be equal to sum over N of phi N of R, phi star N of R prime over omega plus I eta minus En. Ta-dam! Okay, that's exactly what we had for the one particle case in a general one body Hamiltonian. Okay, not necessarily, these are not necessarily plane waves now. They're just the energy, single energy eigenstates. So this is more general than this. This is just for the one body Green's function. I mean, one particle case. But you will see that there's a very analogous form here. If we replace this by a spectral weight, you will see that this is completely general. And now one way to think about this, if you compare with this, you see is that we compare to the one particle case where we can only create on the vacuum. And when we destroy, it gives 0. When we have many body states, you can create in the ground state, but you can also destroy on the ground state because the ground state can contain many particles. So this contains the two possibilities, the propagation of a whole, like in this case, or propagation of a particle. Okay, the two are there. And the only difference is that here there will be a Fermi function, and in the other case, there will be 1 minus a Fermi function. And again, you notice that the Fermi function goes with the energy. The energy is omega. The energy is not k squared over 2m. The energy is omega in general. Okay. So that's it, unless you have some question. Okay, so I will stay if you have some questions, and I will stop the recording. And we'll see you on Friday.
Okay, yeah, bye.